Okay, so we're in section 13.3 now. I think this is actually the longest section in chapter 13. We cover a bunch of different topics here. But the primary two topics are arc length and curvature. So to kind of look back at calculus 2, we're going to start with a result that we've already seen back then. It was an arc length of a curve given by parametric equations. So it's actually chapter 10 of this book that covers this, but you would have covered this in the latter half of calculus 2. So if you have a plane curve C given by parametric equations, x equals f of t, y equals g of t, in that class, in calculus 2, you derive this formula for the arc length of that curve. It turns out that it's an integral formula. It's the if the curve is determined by the parameter interval a, b, these become your limits of integration here, and the length of that curve is going to be the integral from a to b of the square root of the sum of the squares of f prime and g prime. In Leibniz notation, that would look this way. So we're not re-deriving this. It's not worth the time to do that since you've already seen that. But we are going to build some results off of this idea. So one thing to remember is that if you have a plane curve that's given in the form of parametric equations, now that we've introduced vector functions, a vector function is just another way of presenting the exact same thing. So again, if you have these parametric equations, x equals f of t, y equals g of t, then these could be described in the context of a vector function, r of t equals f of t I plus g of t j. This is the same exact curve as this. So that would mean that, you know, if you're looking for the exact same arc length, we could use this formula again. But something worth noting here, the integrand of this this formula here, this integral, is it looks like how we calculate the magnitude of a vector. It's the square root of the sum of the squares of the components of this vector function. So another way of writing that integrand, that square root of f prime squared plus g prime squared, is just as r of t, or the magnitude of r of t, or the norm if you want to use that term. And that gives us a more compact way of writing this formula. Really, it could just be thought of as this way. The length of the arc given by the curve described above is just the integral from a to b of the integral of r prime of t or the magnitude of r prime of t dt. Now, trying to carry this over into the context of space curves, we see that it generalizes really nicely. We're not going to go through a detailed derivation because the derivation will look essentially identical to what you did in calculus 2. But as a reminder of what you do in calculus 2, if you're looking for the length of an arc of a curve, some piece of a curve, in this case a space curve, the approach taken in Calc 2 is to subdivide that curve into a bunch of little sub-arcs by selecting some points along that curve. And then you could connect those points by straight line segments. That's the red here. Those straight line segments, you could calculate their lengths just by looking at the distance between any pair of points used to determine those. We have a distance formula that allows us to do that. And the derivation from here becomes kind of messy because that formula is a little bit messy, as we've seen. But what we would then do is sum all of those lengths and say that's an approximation to the length of this curve. And then we take the limit as the number of those line segments, those approximating line segments, goes to infinity. And that gives us the accurate arc length formula, but also that leads to an integral formula. So in the case of a space curve, we get something that looks essentially identical to the case of a plane curve, just with one extra component. Here's what I mean by that. If C is a space curve, and we have a vector function here giving us that curve C, r of t equals f of t I plus g of t j plus h of t k, then we're going to define the length of that arc C by this formula. The length of that arc C determined by the parameter interval AB by this formula. Notice it looks essentially the same, except we have one extra term here, plus h prime of t squared, or plus dz dt squared if you're using Leibniz notation. Once again, that integrand is the same thing as the norm of r prime. So this little formula is is ideal to work with. It's easier to remember this because this formula applies to both plane curves and space curves when we're looking for arc length. Okay, so let's try an example. We want to find the length of the curve given by this vector function, cosine of t, sine of t, natural log of cosine of t. And when I typed this out, I forgot to write the parameter interval that I was looking for the length of this arc over, but it's t running from 0 to pi over 4. So thinking about what we need, this formula is an integral formula, and its integrand takes the magnitude of r prime. So I should start by finding r prime. What is r prime in this case? R prime of t. First two components are really straightforward. This would just be negative sine of t, cosine of t, and then using the chain rule here, I'm going to get negative sine of t over cosine of t. Although that's the same thing as negative tangent, so let's write that this way. Negative sine of t, cosine of t, negative tangent of t. Okay? So the next thing we need to do is take the norm, or the magnitude of that vector, so we can use it in our integral formula. That's going to look like this. The square root of, so negative sine of t squared, I know that that's just sine squared of t, plus cosine squared of t, plus negative tangent t is the same, when I square it, is the same thing as tangent squared of t. So the negatives don't really matter because everything gets squared anyways. All right, so sine squared plus cosine squared, we know that's equal to 1. I get 1 plus tangent squared of t. And hopefully that radicand looks kind of familiar to you. 1 plus tangent squared is equal to the square root of, well, using that square root there, it's equal to secant squared. We have an identity for that. The square root of secant squared is the absolute value of secant of t. Now, it turns out that absolute value is not going to be necessary, and the reason for that is because of our parameter interval that we're ultimately going to integrate this over. I'm integrating from 0 to pi over 4 in this case, and that entire interval lies within the first quadrant of the unit circle, where all of our trig functions are already non-negative. So that means secant of t is guaranteed to be non-negative on this interval. The absolute value is not going to do anything to it there. So let's find our arc length now. L is going to equal the integral over, now remember the limits of integration are determined by this parameter interval right here, 0 to pi over 4. And like I said before, the absolute value here is no longer really necessary when we consider what the interval that we're integrating over is. Okay, the integral of secant of t is natural log, the absolute value of secant of t plus tangent of t, and we're running from 0 to pi over 4. Okay, what is secant of pi over 4? Well, that would be the reciprocal of root 2 over 2, which is just root 2. So I get natural log of root 2. Tangent of pi over 4 is 1. Okay, and then what do we have now? So plus secant, we're at 0 now, so secant of 0 is 1. So I get natural log of 1. Tangent of 0 is 0, so this is just the natural log of 1. But this is, of course, equal to 0, so that goes away. And we get the natural log of the root 2 plus 1 as our arc length. Okay? So this section in particular, you're going to see that it's going to be really, really important that you remember some of your basic trig identities. This is one of them, the secant squared equals 1 plus tangent squared, but there's others that are going to end up being necessary for some of the problems you do in this section. It's also going to involve a fairly heavy amount of algebra, and that's just because in the vector functions that we work with, once you get to this point where you have the magnitude of r prime, a lot of things are being squared, and then a big square root shows up in there, and there ends up being a lot of simplifying. By this point in your mathematical careers, that shouldn't be that big of a deal, just giving you a heads up, I guess. Okay, so in the example that we just did, we found the length of an arc over a specific parameter interval. That parameter interval was 0 to pi over 4. However, it's kind of useful to determine some other function that will give us the arc length from some specific starting point to any endpoint that we want to use for this interval. In other words, I'd like to turn this endpoint into a variable that I can plug numbers into, and it gives me different arc lengths depending on what that endpoint is. It's a similar concept to when you first learn derivatives. The first thing you learn how to do when you learn how to take a derivative is you find the derivative of a function at one specific point. And that's using that limit definition of the derivative. And then you're told that you can turn the derivative into an entire function of it in its own right, and that function gives you slopes of tangent lines at whatever value that you plug in to that function. So this is kind of a similar idea, and what we're doing is we're coming up with something that we're going to call the arc length function. So once again, C, we're going to let that denote a curve given by some vector function r of t, and we have to fix a starting point on C. It's going to correspond to some particular value of our parameter, which I'm going to call a. So think of a as a constant. Okay, it's a fixed value. What we'd like to do is come up with a function that will measure the length of the arc of this curve that runs from this starting point to some arbitrary ending point that we think of as a variable. So that's simple because we've already come up with an arc length function. All that we would need to do is take our arc length formula, I should say, and instead of running from a to b, let's make that b a variable. Let's call that t instead. If I use a t here, I have to create a dummy variable that I use here for my r prime. So instead of calling this t, I'm going to call it u. So this gives us our arc length formula. Notice the only difference between this and what we defined on this first page here, this guy right here, is that our upper limit of integration is a variable instead of a constant now. Okay. Now something kind of interesting happens here as well. So this type of integral should look kind of familiar to you. In Calculus 1, you talk about the fundamental theorem of calculus, and it's defined in two parts. And part 1 of the fundamental theorem of calculus involves integrals where your upper limit of integration is a variable. If you differentiate this function with respect to that variable, so if you differentiate, say, both sides of this little equation right here with respect to t, the derivative of s of t in Leibniz notation looks like ds dt. And on this right-hand side, the derivative and this integral symbol, in a certain sense, cancel each other out. That's the fundamental theorem of calculus. This variable becomes a t, and we just end up with the absolute value of r prime of t. So it's going to be important to remember this. We're going to use this relationship between the derivative of our arc length function and the derivative of our vector function giving us this curve. And for some reason that didn't come out bolded right there, but that r should be bolded. We're going to use this a little bit later when we talk about curvature. Okay, here's graphically what we're looking at when we talk about this arc length function. So again, we're fixing a value a for our parameter. Remember, when you plug that into your vector function, it corresponds to a position vector, taking me to some point on that curve. And then for any value that I plug into my arc length formula, that's going to give me some specific endpoint on that curve. S of t would then represent the length of the arc of this curve from r of a to r of t, this point to that point. Okay, and you can plug in different values of t to move this second vector around and give you different lengths here. So let's try this with a specific example. What I'd like to do here is find the arc length function for a curve given by this slightly complicated looking vector function. And then we're going to do, as a follow-up, we want to find a point on the curve given by this vector function that's 4 units away from this specific point. Now, one important thing that appears to be left out in the description of the first part of this problem, it says find the arc length function for the curve given by this. But you actually need a little bit more information because, again, the arc length function has to have some fixed lower limit of integration. And there's different choices for what you could put here. But reading the entire question kind of gives you an indication of what we should set that equal to. We want to be, in the application of finding this function, we want to be able to find a distance, or a point rather, that's a given distance away from some specific fixed point. So I want to use this point to determine what my lower limit of integration should be in my arc length function. And comparing this point to r of t, again, by inspection, it's not difficult to see that t equals 0 would give me this point. Try plugging 0 into all of these components, and you should get 0, 1, and root 2 out of that. So everything here corresponds to t equals 0. That's going to be the lower limit of integration that we work with. Okay. Now, with that in mind, let's find r prime. What is r prime of t? Okay. So these are products, these first two components, so we would use our product rule for differentiation. And so this would be e to the t times sine of t plus e to the t times cosine of t if you use the product rule. Factoring that e to the t out gives me this, sine of t plus cosine of t. Okay, there's my I component, plus, next step, I'm going to have e to the t cosine of t plus e to the t times negative sine of t. And so once again, if we factor the e to the t out, I can write that this way, cosine of t minus sine of t there. Okay, and then this, if I take its derivative, is going to be the exact same thing. You're hearing my son in the background, he's very excited. Plus root 2 e to the t. Okay, all right, it's hard to see here, there's a prime there, that's r prime. So now we need the magnitude of this, and this initially is going to look very, very messy. So leave myself some space. What is the magnitude of r prime of t? Well, it's going to be a large square root, and I'm summing the squares of all three of these guys. So what's the square of this first thing here? If I square e to the t, that's e to the 2t. And if I square this, I'm going to get sine squared of t plus 2 sine of t cosine of t plus cosine squared of t. Okay? I know, messy. Plus, now I'm going to square this. So I get another e to the 2t. This time I'm going to get cosine squared of t minus 2 sine of t cosine of t plus sine squared of t. Fortunately, this last component right here squares much more nicely. This becomes plus 2 e to the 2t. And that whole thing is under a big square root. There it is. Fortunately, this stuff simplifies down by a ton. So first of all, if I were to distribute the e to the 2t's in, notice that what would end up looking like 2 e to the 2t sine of t cosine of t is going to cancel with this term over here, because you can see the opposite. So those cancel out. And then if you think about it, what's left? Sine squared plus cosine squared, which is 1. Sine squared plus cosine squared, which is another 1. Times e to the 2t in each case, I get 2e to the 2t when I combine all of this. Plus another 2e to the 2t. This becomes the square root of 4e to the 2t, which is 2e to the t. It looked really, really bad, then turned out really, really nice. So now let's find our arc length function. Okay? Now, what we're going to do here is write s of t equals the integral from, remember, our lower limit of integration is going to be 0. Our upper limit of integration is going to be the t. We make that a variable. My integrand is 2e to the t, except because I'm using a t here, I'm going to change that to a dummy variable, 2e to the u du. Okay? Now what does that equal to? Well, that's just 2e to the t from 0. Oh, sorry, I still need that to be a u. 2e to the u from 0 to t, which is equal to 2 times e to the t minus 1, in parentheses. Okay? So this is my arc length function. Now, to answer this next question, we need to briefly talk about re-parametrizing a curve with respect to arc length. So I'm going to mention that on this next page, and I'm going to come back to this example to work that out. Okay? So we'll probably not get to this example until the next video, but so like we've been saying, the function r of t, the idea of this vector function that we've been talking about all throughout chapter 13, we understand its inputs to be real numbers, and we call that variable a parameter. Okay. However, if you remember from, I guess it's pre-calculus, when you first learn how to parametrize a curve, maybe even trigonometry, one common thing that we talk about with parametrizations of a curve is that there tends to be multiple different parametrizations that are valid. So a single curve can have usually an infinite number of different parametrizations. Now, what does that actually mean for the sake of that curve? Well, depending on how you parametrize a curve, the same point on that curve may correspond to different values of that parameter. And again, it's dependent on how you parametrize the curve. So the parameterization in terms of t doesn't really have much meaning directly to that graph. It just depends on how we choose to parametrize. So the choice of a parameterization may seem kind of arbitrary. Oftentimes we want that parameter to have a little bit more physical of a meaning, something with a little bit more direct meaning, I guess we could say it that way. And so what we're going to do is talk about how to parametrize a curve with respect to arc length, that arc length formula that we just came up with. So if you fix a point on a curve, then you can come up with the arc length formula for that curve relative to that fixed point. And we've been calling that function s of t. Okay. Now it turns out that arc length function, under certain specific conditions, which we're not going to get into, but it's going to be satisfied for the functions that we talk about. This function is actually going to be 1-to-1, which means we can take an inverse of this. And we're not going to describe this in terms of inverses all that explicitly here, but basically that means you can either think of s as a function of t, or you can think of t as a function of s. And what this means for us is if we get an arc length function like we did in the previous example, we can solve that thing for t, and then use that as a substitution in our vector function r, putting r in terms of s instead of in terms of t. We call that parametrizing the curve with respect to arc length. It might be a little bit vague right now, so let's go back to this example and watch what that looks like. Okay, so here's where we found our arc length function. What I'm going to do, I've been calling this s of t, but let's just call it s for the sake of thinking of s as a variable. What I want to do now is solve this equation for t. It's some straightforward algebra there, so I'm not going to go through all of the steps, but basically divide s by 2, add a 1, take the natural log. So I get t equals the natural log of s over 2 plus 1. Okay? This was a 1-to-1 function which allowed me to do this. What do I do with this? Well, the next thing I want to do is parametrize my function up here, r of t, with respect to s. Now that will make it look a lot messier, but that's okay because it allows us to do the second part of this problem more easily than we would have been able to do otherwise. So r of s, what I need to do is substitute this expression in for all of the t's here. Now notice all of the e to the t's are just going to cancel with the natural log, and so what I end up with, I'm going to write this in component form actually, is s over 2 plus 1 times sine of this. This is the part that looks messy. Sine of the natural log of s over 2 plus 1. And then I'm going to have s over 2 plus 1 times cosine of the natural log of s over 2 plus 1. And then finally, this guy doesn't turn out so bad, so I'm going to get s over 2 plus 1 times root 2. Okay, now yeah, that looks a lot worse than what we started with, right? When things were written in terms of t, they were much simpler. But the benefit of having it parametrized with respect to arc length, which is what we just did, we call this re-parametrizing with respect to arc length, is that I can answer this question much more readily. It says we want to find a point on the curve that's 4 units away from this given point. Well, that 4 units away, that's a measure of arc length. We're talking about 4 units along that curve, right? Not 4 units like from one point to another, but 4 units measured along the curve. So that's just the same thing as plugging in 4 for s here, okay? If I plug in a 4, I'll save you all the arithmetic. This just comes out to, sorry, we're looking at well, this would give us a vector which corresponds to a point, so let me actually just write it as a point. 3 sine of the natural log of 3, 3 cosine of the natural log of 3, and 3 root 2. Okay, so this point would be 4 units away from the point given to us up here. So that answers the second question. The first question was to find the arc length formula. We actually did that here, right? And then the work that followed helped us get here. Okay, so a lot of algebra, a lot of solving and whatnot, but ultimately it's nothing you haven't seen before. That's going to be all the time for this first video.